This is edexcel core pure 1 proof by induction chapter 8. Let's do this mixed exercise with the flag EMP. Number 1, the proposition is 9n minus 1 is divisible by 8 for all positive integers. So the first step is n start with 1. So 9 to the power of 1 minus 1 equals 8, which is divisible by 8, so it's true. N equals k, so this is assumed. 9k minus 1 is 8a. This is the way of the express the divisible by 8 or multiple of 8. So but you need to give the restriction for this. So now we know k is z plus, and a also should be integer z to be to express the divisibility. So when n is k plus 1, 9k plus 1 minus 1 equals 9 times 9k minus 1. Induction should the step 3, which is this one, should be proved by using the second step, this assumption. So 9 to the power k from here is 8a plus 1 minus 1. So 9 times 8a plus 9 minus 1, which is 8, 9a plus 1, which is true. So here and here, because the first step and third step is proof, the second step is assumption. So assumption doesn't need any conclusion of this step, but the first one and the third one need the conclusion within the steps. And the last one, since P1 holds and Pn plus 1 holds, when Pn, Pk plus 1 holds, when Pk holds, is true. By mathematical induction, Pn holds for n z plus. Number 3. Induction, all positive integers. So proposition is sigma r equals 1 to n, 3r plus 4 becomes 1 over 2n, 3n plus 11 for n positive integers. So n equals 1, left-hand side, this is left-hand side, this is right-hand side. So left-hand side equals r equals 1 to 1, 3r plus 4, means 3 times 1 plus 4 and 7. LHS 1 over 2, 1, 3 times 1 plus 11, so 1 over 2, 1, 14, which is 7. LHS, therefore, it's true. When n equals k, this is assuming assumption. That r from 1 to k, 3r plus 4, you need to be careful or what is k and what is n and what is r here. R is dependent on the sigma notation. So this and this. So this that we don't control r as a variable for the whole expression. So only n becomes k here. And n becomes k, 3k plus 11. For k, z plus. You should mention this. N equals k plus 1. Sigma r 1 to k plus 1, 3r plus 4. As I told you, it should come from the second step, the assumption. So I will separate it. 1 to k, 3r plus 4 plus 3k plus 1 plus 4, like this. Because I can use this one now. 1 over 2k, 3k plus 11, plus 3k plus 7. So now I'll make 1 over 2, because anyway, even so now we are going to here 1 over 2 k plus 1, 3k plus 14 eventually. So we are going there. So we need 1 over 2. So just let me make it 3k squared plus 11k plus 6k plus 14. 1 over 2, 3k squared plus 17k 17k plus 14. So now k, 3k, 17, 2 and 7. So therefore 1 over 2, k plus 2, 3k plus 7. Oh no, this doesn't make 17. 14, 1. K plus 1, 3k plus 14. Just to make the consistent expression, so 1 over 2, k plus 1, 3k plus 1 plus 11. Then we figured it out. Now our result is accordingly here. When we input k plus 1 into into n, then we have this result. So it's true. So the final conclusion is the same. Since P1 holds and Pk plus 1 holds when Pk is true, by mathematical induction, Pn holds for n is Z plus. And number 4, now we have matrix n given. So Pn equals a to the power of n, 8n plus 1, 16n, negative 4n, 1 minus 8n, when n is Z plus. So when n equals 1, a to the power of 1, this is again LHS and RHS. A to the power of 1, and we know that is 9, 16, negative 4, and negative 7. RHS, 8 times 1 plus 1, 16 times 1, negative 4 times 1, 1 minus 8 times 1. 9, 16, negative 4, and negative 7. LHS equals RHS, therefore true. When n equals k, assuming that a to the power of k becomes 8k plus 1, 16k, negative 4k, 1 minus 8k. 4k is Z plus. N equals k plus 1. So now we need to make it ak plus 1 becomes ak times a. So ak plus 1, 16k, negative 4k, 1 minus 8k times 9, 16, negative 4, and negative k. So like now, 72k plus 9 minus 64k, and 8 times 16k plus 16 minus 16 times 7k, and negative 36k minus 4 plus 32k, and negative 4 times 16k minus 7 plus 7 times 8k. So this and this 8k plus 1. This and this is 16k. It's like 8x minus 7x, so it's 16k plus 16. And this one negative 4k And this one, no, I mean minus 4. And this one, again, negative 8 times 2k, then 8, 5. Negative 8 times 8k, so negative 8k minus 7. So therefore this is expressing like 8 to the power of the first one plus 9, k plus 1 plus 1, 16k plus 1. And negative 4, k plus 1. So negative 8, k plus 1 plus 1. So just to make the consistent form, 1 minus 8, k plus 1. So this is exactly the same form that we have here. Instead of n, we put k plus 1. So we got the result. So it's true. Therefore, the result is the same. Since P1 holds and Pk plus 1 holds, when Pk is true, by mathematical induction, Pn holds for n includes in Z plus. So let's go for the number B. So number B, hence find the B in terms of n. So B is a to the power of n negative 1, inverse. So 8n plus 1, 16n, negative 4n, 1 minus 8n of negative 1. So determination, before the determinant, 1 minus 8n, 8n plus 1, negative 16n, 4n. And determination of an, 1 over. So determination of an is ad. 8n plus 1, 1 minus 8n minus bc. 16n times 4n. So this is 1 minus 64n squared plus 64n squared. Oh, which is 1. So therefore, the last answer is B equals 1 minus 8n, negative 16n, 4n, 8n plus 1. Number 5. The function defined f of n like that, and a f n plus 1 minus f of n, 5 2 n plus 1 minus 1 plus 1 minus 5 2n minus 1 plus 1, like this. So 5 2n plus 1 plus 1 minus 5 2n minus 1 plus 1, no, I mean minus 1. So the smaller one, 2 to the 5 to the power of 2n minus 1 is smaller. Then now we have 5 to the power of 2 minus 1. So 24 times 5 2n minus 1. So number B. Prove by induction Fn is divisible by 6. So proposition is Fn is divisible by 6 when n is positive integer. So n equals 1, 5 to f of 1, 5 to the 2 minus 1 minus 1 plus 1, which is 6. Therefore, it's true. And k, assume that f of n, f of k, 5 to k minus 1 plus 1 equals 6a, where k z plus na should be integer. And n equals k plus 1. F of n plus k plus 1 equals 5 to the 2 k plus 1 minus 1 plus 1, and 5 to the power 2k plus 1 plus 1. Because I want to deduce like this, so 5 to the power 2 and 5 to k minus 1 plus 1. 5 to the power 2 and 6a minus 1 plus 1. And 5 squared 6a minus 24. Therefore 6 25a minus 4. True. And the result is the same. Therefore, since P1 holds, what am I doing? P1 holds and Pk plus 1 holds when P and Pk is true by mathematical induction. Pn holds for and Z plus. So let's go to the number 6. Prove by induction 7 to the power of n, 4 to the power of n plus 1 divisible by 6. So proposition is 7 to the power of n, 4 to the power of n plus 1 is divisible by 6. Actually, you can start like this. And n is positive integer, a should be integer. So P1, n equals 1. 7, 1, 4, 1 plus 1 is 12, is 2 times 6. Therefore, true. When it is divisible by 6, you need to express it 6 times something. And you need to understand 0 is multiple of all numbers. Because if we have the answer here, 0, let's say, then 0 times 6. So 6 times integer. So this is multiple of 6. But now we have only 12. And when equals k, assume that 7 to the power k, 4 to the power k plus 1 is a 6b here. Because a was more general expression with k with n. But now we change into k. So we need to change it into b. So now it's the same, k, z plus b, z, and nk plus 1. 7 to the power k plus 1 plus 4 to the power k plus 1 plus 1. My case, 7, 7k plus 4, 4k plus 1. My approach is I change the most complex one. Yeah, among those expressions like 7 to the power k, 4 to the power k, I select 7 to the power k. So instead of 7 to the power k, I put 6b minus 4 to the power k minus 1 plus 4, 4k plus 1. Then 6 times 6b minus 6 times 4 to the power k minus 7. Oh, 7. Plus 4, 4 to the power k plus 1. So 7 times 6b minus here negative 3 and 4 to the power k minus 6. So 6, 7b minus 4 to the power k is 2 to the power 2k. And we need to make it 6, we need another 1, 2. So 2 to the power 2k minus 1, minus 1. So this is also expression of 6 times something, so it's true. And this is something means integer, so it makes sense. So since P1 holds and Pn plus 1 holds when Pk is true, mathematical induction, Pn holds for nz plus. N7. I have another 3. proposition is, so, and also here, we don't call it proposition equals like this. Proposition is statement. So it's just this whole statement. To A, 1 to n, r plus 4 equals 1 over 6, n plus 1, 2n plus 13, when n equals positive integer. So here, n equals 1, sigma LHS, sigma n equals 1 to 1, r plus 4, means 1 times 1 plus 4 is 5. LHS, 1 over 6, 1, 1 plus 1, 2, 1 plus 13. 1 over 6, 1, 2, 15, 5. So LHS, therefore, true. N equals K assumption, assuming that R starts 1 to, why this doesn't look like R? Starts from 1 to K, R plus 4, becomes 1 over 6, K plus 1 to K plus 13, where K is Z plus. So the next step, K plus 1, so LHS, R equals 1 to K plus 1, R plus 4, so we separate it from 1 to K, and the last one. 1 K plus 1, K plus 1 plus 4. So this one, by assumption, we have this result. So 1 over 6, K plus 1 to K plus 13, plus K plus 1. But just intentionally, I make it 6 over 6, K plus 1, K plus 5. Now we have commonly 1 over 6 and K plus 1. And the remaining things is K, 2K squared plus 13K, plus 6K squared plus 6K plus 5. 1 over 6K plus 1. 8K squared plus 36, 49K plus 30. So 2, no, I made a mistake because K plus 1 is not there. So here is just K plus 5. So 2K squared plus 19K plus 30. Or 15 and 2. So 1 over 6, K plus 1, K plus 2, 2K plus 15. Therefore, 1 over 6, K plus 1, K plus 1 plus 1, 2K plus 1 plus 13. Therefore, true. The result, the last conclusion is, since P1 holds, PK plus 1 holds when PK is true, mathematical induction, Pn holds for and Z plus. Number 8. Proposition is sigma r from 1 to 2n, r squared is 1 over 3, n 2n plus 1 for n plus 1. So n1, LHS, 1 to 2 r squared is 1 squared, 2 squared, which is 5. LHS, 1 over 3, 1, 2, 1 plus 1, 4, 1 plus 1, 1 over 3, 1, 3, 5, which is 5. LHS, LHS, therefore true. And K, assume that sigma R1 to 2K R squared, 1 over 3K, 2K plus 1, 4K plus 1, where K is Z plus. Oh, I didn't mention here. K should be in Z plus. It was my big mistake because without this one, there is no reason to start with n equals 1. So that is the like flag of this starting point. And when n equals k plus 1, LHS sigma r 1 to 2k plus 1 r squared becomes 1 to 2k r squared plus 2k plus 1 squared plus 2k plus 2 squared. So 1 over 3k, 2k plus 1, 4k plus 1, plus 2k plus 1 squared plus 2k plus 1 squared, which is 4. Any, none of them has any clue here. So just because we need 1 over 3, just let me make it 1 over 3. And here I need to expand them all. 8k squared cube, 6k squared plus k, plus 4k squared, 4k plus 1, 4k squared, 8k plus 4, 1 over 3, 8k cube, plus 14k squared, plus 13k plus 5. So here oh no, I made mistake. When I make it multiply by 3, I'm multiplying by 3 them here. Sorry. So 8k squared plus 12 and 12, 24, 30k squared, and 12k, 24, 36, 37k, plus 12 and 3, 15. Did I make it well? Then now it's easy to guess. This has negative 1 as a root. So 8, 30, 37, 15. Negative 1. 22. Negative 22, 15. Negative 15, 0. So 8k squared, 22k plus 15. 2, 4, like this. So 1 over 3, k minus 1, no, I mean k plus 1, and 2k plus 3, and 4k plus 5, which means 1 over 3, k plus 1, 2k plus 1 plus 1, 4k plus 1 plus 1. So it's true. Therefore, the last conclusion is same. So number B, given This is the same. So now we have from our induction, we already know the left side 1 over 3 and 2n plus 1 4n plus 1 equals k. R squared is 1 over 6 n plus 1 2n plus 1. If I remember it well, then we can multiply by 6 on both sides and k must satisfy. Okay, so let's bring it over here. 2n plus 1 4n plus 1 minus kn n plus 1 2n plus 1 equals 0. So n plus 1 2n plus 1 is common, and 2 4n plus 1 minus k n plus 1 should be 0. So this cannot be 0, this cannot be 0 because n is positive integer. So only this can be 0. 8n plus 2 minus kn minus k equals 0. So n equals k minus 2 over 8 minus k. So 2 minus k over k minus 8. Number 9. Matrix has the induction, okay, proposition is m to the power of n, cn, 2n, en, 2n minus 1 over c, 0, 1, for n is positive integer. So n equals 1. Left hand side, m to the power of 1, which is 2c, 1, 0c as given. LHS. C to the power of 1, 2, 1, 2, 1 minus 1 over c, 0, 1, which is 2c, 1, 0, c. LHS, RHS are equal, therefore true. When n equals k, assume that m to the power of k, ck, 2k minus 1 over c, 0, 1, where k is z plus. N to the power of k plus 1, m to the power of k plus 1 means m to the power of k times m. So c to the power of k, 2k minus 1 over c, 0, 1 times m, which is 2c, 1, 0, and c. So c to the power of k is just a scalar, so we can multiply like this. So 2 to the power of k plus 1 times c, and 2k times plus 2k minus 1, and 0 and 0, and 0 and c, like this. So c to the power of k, 2 to the power of k plus 1 times c, and 2 to the power 2k plus 1 minus 1 over c times c, 0, 1 times c. So we can take out 1c from matrix. So ck plus 1, 2 to the power of k plus 1, 2 to the power of k plus 1 minus 1c, 0, and 1. Just to make the consistent expression. So it's true. Therefore, P1 is true and PK plus 1 is true. When PK is true, mathematical induction, Pn holds for n equals z plus. So number B, determinant m to the power of n is 50n. So, okay, so AD minus BC. A D minus B C equals 50 to the power of n. So this is c to the power 2n times 2n becomes 50 times n. So 2 times c to the power of 2n equals 50 n. So 2 c squared becomes 50. C is positive integer 5. C is positive integer. That's it.